Hi everyone, I'm going to go through some simple harmonic motion intro stuff. This is my schedule and it's going to be posted on my website. To find the packet for simple harmonic motion, you click this giant SHM packet and it'll take you to the packet. This is where you're going to find all of your homework assignments and the notes that I'm going to go through right now. So I am going to start the notes on page, let this thing load. Here it is. Anyway, this is it. These are all your things. We're eventually going to do this AP problem from 96. And here is the video notes that you guys will take. And here's like a summary of everything that we're going to talk about. And we're going to start the notes on page 5. Okay. So either you can print this out and take the notes at home, or you can do this simply in your notebook. Okay, so here I am. This is page 5. And we're going to talk about simple harmonic motion. What that means is we're talking about specifically what we're going to talk about in AP Physics 1 is things oscillating in such a way that they make a sinusoidal wave in terms of their position, velocity, and acceleration time graphs. So what I mean by that is, I'm going to do some screen sketches here. Okay, let's say I have a spring attached to a wall, which is attached to a mass. And that spring is currently at equilibrium. So this position, x equals 0, I'm calling equilibrium. Okay, if I pull this mass right here, it has potential energy to move forward. Okay. If that mass was here instead and was compressing the spring, it also has some potential energy. Don't forget that potential energy is US equals 1/2 kx squared, where k is your spring constant. And the unit for that is newtons over meters. X is the distance away from equilibrium. And we measure that in meters. And this is your energy, which is measured in joules. Okay. So when we talk about simple harmonic motion, we're talking about what this position time graph would look like. Okay. And a couple of things I want you to note before we get into this in detail is it's important to understand that when I pull this block to a certain location, this is, let's say, the max position this block can reach. Okay, so I'm going to call that my amplitude. Okay, and this right here is the max position that it's going to be compressed. So this is my negative amplitude. Okay. Now, when I pull this to this location, I'm going to do this in a different color actually. The velocity at this point is equal to 0. And as it passes through here, it's going to get faster and faster. So I'm going to actually draw a dot chart. It's going to get faster and faster and faster. And then it's going to slow down again until it reaches the negative amplitude, and velocity again is equal to 0. Okay, so it's important to understand that your velocity is obviously not constant. Now, if it was, keep in mind that your position time graph, if velocity was constant, would be a bunch of straight lines. Okay, that's not the case here. It's not constant, so you're going to see lots of, this is your position time graph, you're going to see lots of curves. I'm not going to draw those yet because we're going to get into that in a second. Okay, So velocity is not constant. You see that velocity is 0 at the max positions, also known as the amplitudes. And you see that at this point of equilibrium, if velocity is 0 here, think about how fast would it actually be going when it hits the center of equilibrium, when it's going back and forth, back and forth. That back and forth motion we call oscillation, okay? When something moves back and forth. Okay, the two major things we're going to be talking about are masses on springs, and the other big one is a pendulum. Now, I don't remember if we've ever talked about pendulum before. If you were in the summer workshop, I think we did pendulum in that workshop. So we're going to be talking about a bob that goes back and forth. If you remember in class, I did the bowling ball thing, which kind of, I mean, we barely talked about it, but that's basically a pendulum. Okay, so this is what we're going to talk about. So we're going to get right to the notes. Okay, so, and this kind of talks about different types of simple harmonic motion. So when you have a spring that's attached to a mass and it reaches a point, let's say I take this mass and I stretch it all the way out here, and this distance is x, and we're also calling this point the amplitude. What naturally wants to happen is that there's a restoring force, okay? This spring wants to get restored back to equilibrium. So that is the force, a restoring force. Wants to get this mass back to equilibrium. Okay. So the first thing, this is your first blank right here. It says blank is a point in an oscillatory system where the force is equal to 0. Okay. That restoring force that we're talking about, when is that force equal to 0? Well, when it doesn't need to be restored. So where is that actually happening? That's happening at this point when x equals 0, which is equilibrium. Okay, so equilibrium is that point where their force is equal to 0. So your second blank, restoring force, is a force that pushes or pulls an object back towards the equilibrium position. It's proportional to the displacement away from equilibrium position. So that force is equal to negative k times x. K is still your spring constant. And this is where the unit makes more sense. Newtons over meters. That's easy to understand in this equation because your force is measured in newtons and your displacement is measured in meters. X is the distance away from equilibrium. Okay. So going back to my original picture, and I'm going to go back and forth. So I'm not sure if you guys have blank space on your pages. I write pretty bubbly, so this is not enough for me to work with. Well, actually, I can draw it back here, but my original picture was over here. So the first thing it says is a time to complete one full cycle. Okay, so let's talk about one full cycle. What does that even look like? So using this original picture, one full cycle would be let's say I was starting here. It'd be going this way, back again, and then back to the original position. Okay, so how many amplitude is this block traveling to actually get to one full cycle? We have one here, another one here, that's 2, 3, 4. Okay, so 4 amplitude to get up to one's full cycle. Oftentimes when we talk about displacement though, typically the block starts at this point of amplitude. So it's like it has 1 amplitude it travels, then another, going to the minimum, going back to equilibrium, and then going back to the maximum. The point when it starts to repeat itself is the period of time. So that's the time it takes for one cycle. So that's called, that is called the period. Oh my gosh. Okay. And the number of cycles per second is the inverse of that, which you remember, I hope you remember, is the frequency. So the way to relate period and frequency is right here, t equals 1 over f, or you can write the inverse of that, which is 1 over t equals f. And don't forget, frequency is measured in hertz, period is measured in seconds. Okay. So I just talked about this. So when we talk about the restoring force, that's negative k times x, this equation is called Hooke's law. Okay, and it's the restoring force in a horizontal mass spring system. Okay, so it says constantly that it's proportional to the distance from equilibrium. So what that means for us is if that distance goes up, that means there is more force that needs to be pulled back to equilibrium to restore that block back to that position. Okay. This is a nice little graphic of it. You see that when it's in the positive location, so this negative sign is important because if I go in the positive x direction, which way is that force pushing it back? Okay, so if this is positive x, that force is pushing it back in the negative direction. And that's why that negative sign is there. It kind of makes us remember, okay, if it's going in the positive x direction, the force is going to pull it back in the negative direction. If it's being compressed and that x is being pulled back, that force is going to go push in the positive direction. So this is a nice graph because when the x is positive, you see that the force is negative. Okay, and when x is negative, like right here, this is all negative x, you see that force is above 0 and vice versa here. I want you to think about that. Okay, so the object's maximum displacement from equilibrium is called the amplitude. So the object's position oscillates between negative a and positive a. So as you can see in this picture here, this right here is equilibrium. So I'm going to write x equals 0. Okay, so at this point, the block was stretched to the amplitude. So you see that at this point, it comes over here, and then it curves downward. The position now is at x, and then it gets to this point of negative a. So you can see that it curves back and forth. Now, you might ask yourself, well, why isn't it a straight situation like this? Well, it's not, because as we talked about, this would imply, so I want you to think about what this graph, this basically is your position time graph. Okay, so if you were to rotate this, so basically I can take my tablet and rotate it. I can't do that for you, unfortunately, right now. But if I were to rotate that, that would be a position time graph. That's pretty easy to understand. Okay. Now, if this was my position time graph, this is, let's say, my x and my t, these straight lines would imply that it's constant velocity. And as we talked about here, velocity is not constant. Okay, we know that we should be seeing curves, hence these curved graphs right here. Okay, so the first question says, what values of x is a force the greatest? Okay, the force is going to be the greatest when it's farthest away from equilibrium. So that's going to be at A and negative A. What values of x is acceleration going to be the greatest? Okay, well, this helps us bounce back to our most famous equation, net force equals mass times acceleration. If I have a restoring force, that means when x is greatest, that means A is going to be greatest. Okay, even though we know that at the point when it's oscillating at the amplitudes, it's not velocity is equal to 0 because that's the point when it's turning around. That doesn't mean acceleration 0. Actually, on the contrary, acceleration is the greatest at these amplitudes because it's proportional to my restoring displacement. Okay. Now, when is x, the values of x, what values of x is the speed the greatest? Okay, well, we talked about that briefly here. Now, at the endpoints, the amplitude's velocity is equal to 0, so it's getting faster, faster, faster. Look at my dot chart. You can see that at equilibrium, it's going to go the absolute fastest. Okay, then it's going to start decreasing speed as it gets closer to my my negative A. And then it's going to repeat that entire cycle over and over again. So at what values of x is this be the greatest? Well, x equals 0. Equilibrium. When is velocity equal to 0? At the endpoints when it's turning around. I'm going to say turning around. And you can relate this to when a ball is thrown up in the air and it reaches a max point. At the very max point, it starts to turn around. So velocity is equal to 0 there. And what values of x is the acceleration equal to 0? I want you to try that for yourself first. If x, so when is force equal to 0? Well, force is equal to 0 when x is equal to 0. And if force is equal to 0, that means my acceleration has to be 0. So when x equals 0 at equilibrium, my acceleration equals 0. Okay, I'm going to keep going forward. And I think you'll find that a lot of this is going to be on these pages, like 7, 8, 9, whatever. It's going to be a little bit repetitive. This is from the textbook, the Knight textbook, which you don't have, but it's just old notes from the textbook. So it says the instantaneous, and don't forget, instantaneous velocity is at a specific moment. The instantaneous velocity is 0 at the points positive and negative A. These are the endpoints of the motion, aka amplitude. Okay, now this is the kind of graph you're going to see more often. So in the previous slide, that graph was oriented 90 degrees right here. Okay, so now we're just going to flip that graph. So you're going to see a graph like this. And all of you guys should recognize what type of trig function this is. You're starting at some amplitude. So your options are sine x or cosine x. And we'll talk about what that is in a second. So whenever it starts at an amplitude that's not 0, we're going to use cosine x. Okay. So this is a position time graph. And this point means that the block has been starting at when the block is here. So we're going to say this is the starting point of my cycle. Then it's going to go back and forth, back and forth, back and forth. Okay. So typically when you see a position time graph for a block, it's usually oftentimes in AP Physics 1 starting at that amplitude of A right here. Okay. So what that means for us is this right here is the amplitude, and this is where it's starting at t equals 0 seconds. So at t equals 0 seconds, my block is going to start moving. And it's going to go back and forth, back and forth, back and forth. Okay? I'm going to actually draw a picture of that. Okay. So my block is here. It's attached to a spring. And this is equilibrium right here. It's going to go back and forth. So really, this is not like vertical. This graph is shown like this because this is how we have to draw it in terms of our XT graph. Okay, so then we've talked, so this is your position time graph. So ask yourself, if your block is starting at the end point, and this right here is equilibrium, and this right here is A, this is X equals 0. And let's say this is the other endpoint, negative A. If we're starting right here, what is the velocity at this point? And you should know that it's 0, right? So here's your graph. Velocity is equal to 0 when my amplitude is here at t equals 0. So this is the matching velocity time graph of this position time graph. Okay, maximum speed Vmax is reached as the object passes through equilibrium. The velocity is positive as the object moves to the right, but negative as it moves to the left, because it's going in the negative direction. Okay. So now we're going to fill in some of these things. You should actually perhaps pause the video and see if you can fill this in on your own. Okay. So when my position, so I would say pause video now and figure what these are. So if at time equals 0, this is your position time graph. Okay. This is your period right here. So this is when it starts to repeat itself. So this is 1/4 times t. This is 1/2 times t. This is 3/4. You can't really see those fractions. So this is 1/4, 1/2, 3/4, the period. Okay. So at time equals 0, I am at amplitude. What is my velocity? Well, think about that. That's got to be 0. If you're at a positive acceleration, which is what can you say about the acceleration? Well, I can say that it's going to be accelerating. So I'm going to call that my max acceleration. And because it's pulling it in the opposite direction, I'm going to put a negative sign here. So they're going to have negative acceleration pulling the block down this way. Okay. So again, at equilibriums, I know that this is going to be the maximum velocity. And if x equals 0, that means my restoring force is 0. So that means my acceleration is 0. So anytime I see 0, I can put that in there. And then if I have a block and this is equilibrium and it's been compressed at this point, it went to the point of negative A. This is x equals 0. So which way is the restoring force going to make it go? Well, it's going to make it go this way. So it's going to speed up in the positive direction, speed up in the positive direction, which we know is a positive acceleration. This, by the way, is 0. At amplitude, velocity 0. And this would be, again, negative A max, because then I'm going to start repeating. Okay, so how do we write this in terms of equations? Well, this is where we are going to get into derivatives. So if you are taking calculus, this will be nice for you. For those of you who aren't in calculus, you're going to have to memorize this little box here. Okay. I'm going to continue this part of the lecture in another video, just because I feel like this is a good stopping point. But what I do want to say is this is your equation for your position time graph. A means amplitude, and this is a function of time, which means that that time is right here in this equation. So when we think about this, one way I can write 2 pi over t is I can also write it like this: x of t equals a cosine omega t, because you know that omega equals 2 pi over t. Okay, so you also know that omega equals 2 pi times f, which gets to your other part of the equation, which is this thing right here. Okay, so again, I just want to say that this equation is something you'll have to memorize. Another way to write it is writing a cosine omega t. All right.